same thing, 1. And I can't get anything outside of WW. So you can beat me there too. How can I nail you down so you can't do that? Why are you winning? It's because you can get the V and the X, each of them, to be identical things on the left and the right half of this string. And I can't stop you from doing that. Not with this bad string. How can I stop you from doing that? Stick some P's here. How does that stop you from making the V's be, say, 3 zeros here and the X's be 3 zeros there? I mean, Erica's got exactly the right idea. This'll help me. It's because the VWX part is supposed to be less than or equal to that number that you gave me originally. That's the constraint. We started from the bottom. We look for the first duplicate, so that VWX middle section has to be relatively short. You can't just say that there's V's that are 2 zeros here and X's that are 2 zeros there, because that would span an area that's too long. It would span over all the P1s plus some extra symbols, and that's bigger than P. So if you're stuck with this condition, then the cases here, I can win every single time. If you pick VWX all in zeros, then I can pump them up and get the first half different than the second half. If you try to straddle them around these zeros and ones, I'll get something like this. 0 to the Q, 1 to the Q after I pump it. 0 to the P, 1 to the P. But now the first half's not the same as the second half. Q is bigger than P. The half is in the middle here. And you can go through every single case. Imagine that you're taking P symbols at the most length and shifting it left to right. It can be all in the zeros. It can be over the border of the 0 ones. It can be in the ones, over the next border, in the zeros, over the next border, in the ones. It's going to be 1, 2, 3, 4, 5, 6, 7 cases. All the arguments are similar for each of these cases. It makes the half and half lopsided. But they're all the same kind of argument. I can pump it up with one extra pump, I equals 2. So that's a good idea, putting those P's in there. And you'll notice that this is a very big deal. Without this constraint, I can't win the game. And that's why we go from the bottom to the top in doing that pumping lemma proof, so I can guarantee that that constraint actually is there. Well, let's try a language that I won't tell you whether it's context-free or not. We'll try to prove whether it's context-free with a pumping lemma. And if we don't get anywhere, maybe we'll conclude that the pumping lemma actually, that the pumping property actually holds for that language. Maybe that'll make us think that it is context-free. Let's try. You shouldn't be able to win the game if the language really is context-free. Right? The pumping property works then. So the contrarian trying to show you that the pumping property doesn't work, they shouldn't be able to succeed if you start with a context-free language. The only reason I won here is because we started with a non-context-free language. So let's pick a language maybe that is context-free and show that I can't win no matter what I try to do. Maybe that'll make this idea a little more clear. All right, so somebody pick their favorite context-free language, or should I pick one? Who wants to pick one? It's got to be your favorite. It can't just be any context-free language. Palindromes are your favorites?
Sure.
All right. Are there 2 L's in palindromes? Why? All right, let's do palindromes. So somebody in the class doesn't believe that palindromes are context-free, and they want to convince you that they are not context-free. And that person is me. All right? And I don't care that you showed me a grammar or a machine. I still say they're not context-free, and I'm going to prove it to you with the pumping lemma. And I'm not going to be able to win this game unless you guys make a mistake. So you shouldn't make a mistake. You have to do your part well. OK, so you say you have a grammar that accepts palindromes. And I say, how many non-terminals does it have? You actually do have a grammar this time. So how many non-terminals does it have? Yeah? Can you do it with less? Chomsky normal form. We don't. Yeah, let's say 5 or 6, whatever. All right, so I pick strings that are bigger than 2 to the 5th or 2 to the 6th. Let's call that strings bigger than size p, and I'm going to give you this string. 0 to the p, 1 to the p, 0, 1 to the p, 0 to the p. Okay, there's a palindrome. And now you split it into 5 parts, and then I'm going to win. Well, I won't be able to win if you split it into a good 5 parts. How can you split this into 5 parts, identify the v and the x for me, such that no matter what I try to do with the pumping, it always still ends up as a palindrome? In other words, I can't convince you that your grammar accepts anything except palindromes. Where should the v and x be? Where should they be? You can make the v some number of ones here, and the x some number of ones here, the same number. And fiddle with the w and the u and y any way you want to get the rest of the symbols. Then whenever I pump it, I'm just going to get 0 to the p, 1 to the q, 0, 1 to the q, 0 to the p. Just more ones on each side, equal numbers. And it's still a palindrome, and I'm dead. So I'm going back to the drawing board. Okay, I'm not going to let you do that this time. I'm going to make the 0 to the p this time. Remember, that was Erica's trick last time, so I'm using Erica's trick again. So now tell me where the v and x are. Now I think I'm going to win. They can just be in the middle here, right? No matter what I do, no matter what string I pick, every single string I pick, every single one, can be divided into 5 parts so that VWX is smaller than the p, so that whatever I pump it up, and any I up to infinity, it will always end up being a palindrome. That's what the pumping lemma says. And it's true because of the structure of this grammar. I'll never win this. So that's a good way for you to see whether you have one. If I picked something that wasn't context-free, you should be able to win in this long argument. It's somewhere along the way in the adversarial back and forth. And the way you should write it out is as formal as you feel comfortable with. It can be just a page of English explaining the dialogue and how you convince the other person that when you finally pump it up, you get something not in their language, no matter what they do. And if there's many cases involved, then divide it into those cases and carefully enumerate them. And if all the ideas are the same in all the cases, just say, okay, this is the same as the case before. You can see that. You can shorthand what you're doing, but make sure it's nice and clear. All right, are there questions about this? How about this? Last one. We did this with regular sets. Just numbers of zeros that have a square value. So 0, 0 to the 4th, 0 to the 9th, 0 to the 16th. Is that set context-free or not? It wasn't regular, and now I wonder whether it's context-free. What do you think? You think no. Or if we think no, then we've got a proof to do. So let's try to do this with the pumping lemma. If we fail with the pumping lemma, maybe we'll be more convinced that it is context-free and go back to the drawing board and try to do a grammar. And that's a good thing about these kind of things. You never actually fail, because when you fail on one side, you go back and work on the other side. Or maybe yet, if you're a pessimist, you're failing twice. But I like to think of it that you always got something else to try. Okay, so 0 to the x squared. Somebody picks the number of non-terminals in the alleged grammar. We raise it to the power of 2. They tell me that value is p. I have to pick something that's bigger than p symbols, that's in this language. And since I got no better idea, and I have no idea if this is going to work or not, I'll just do the obvious, 0 to the p squared. That's got way more than p symbols. It's in the language. Now you split it into 5 parts, such that the VWX part is less than or equal to p symbols. Well, there's only one symbol in this alphabet, just 0. So basically, you're going to tell me how big that middle part is. How many zeros are on the v part? How many zeros are on the x part? And the total of the v's and the x zeros altogether is going to be, at most p. Okay? Well, I'm going to have to handle any number you give me, from 1 all the way up to p. And whatever number you give me, I'm going to show you that I'm going to pump it up one time and it won't be a square. Okay? Right now, UVWXY is 0 to the p squared. What's the range